Okay, so what we'll be doing in the rest of this class today, and then a lot more on Wednesday and the week thereafter, is we'll talk about kernel methods. And the thing is that kernel methods require a fair amount of convex optimization. And since this is going to be useful not just for kernel methods, but also for pretty much anything else you're going to do in your PhD or master's degree or whatever, I would, we'll basically start with a little bit of optimization. I would say if you want to know more about this, I would strongly advise that you take the convex optimization class that's being offered, I think, by Geoff Gordon and Ryan Tibshirani. And yeah, it's a pretty fun class. Okay, so what are we going to do? We'll start with convex optimization and just, unconstrained problems, then constrained ones, and then we'll delve deeper into linear and quadratic programs. The Boyd and Vandenberg book is actually a wonderful source for a lot of this. It's freely available, so you can, and there actually pointers to this all in the slides. You can also buy the book if you want to do those guys a favor. It's not very expensive. It's like $60 for 600 pages, which is a pretty good deal. Then we'll cover support vector machines, and we'll finish up with kernels. So probably today we'll get through the unconstrained optimization part, but don't worry, the rest isn't that scary. So if you do unconstrained optimization, you need, at least in our case, we'll need a little bit of convexity. So I guess everybody knows what convexity is, right? Or at least you've probably heard about it at some point. Let's start with a convex set, just in case. So a convex set is really just this beast where if you, have a set, and you can draw, like so, and you can draw a line between 2 points in the set, then the entire line has to be inside the set. As long as you can show that, the set is convex. If you can't, then you can't. So, like, if you have Pac-Man, then, well, it's not convex. Okay, easy way to remember. A convex function is one where the epigraph is convex. In other words, I do this, draw a line, and this has to be below. Right. This is the poor man's introduction to convexity, and you can actually derive a lot from that. These are the equations for that, and there's one lambda too many, so please cross that out later on. Right. So this is just saying this is the linear interpolation lambda f of x plus 1 minus lambda f of x prime. This thing here. This is greater to equal than f of lambda x plus 1 minus lambda x prime. So remember the pictures. You can always work out the equations on your own. That's not hard. Okay, there we go. Below set, yes. Now, here's a really nice reason why a lot of people like convexity. Because in many cases, the problems tend to be easy that arise from convexity. Well, easy is a relative thing, right? Easy can still mean NP-hard problems if you have a graphical model and, you have an exponential number of parameters to sum over. But at least you know that the minimum has to be unique, as in the minimum value, not necessarily the minimizer. Okay. So the first thing to notice is that, just proved by contradiction, if I have a non-convex function, or if I had two local minima, right, then this function could never ever be convex, right? Because I can just draw this line, and I know that the graph of the function has to be below. But if I have two local minima, then in between there, something has to be larger than any of those two minima, so I'm screwed. Okay. Question: can somebody tell me a function that has more than one global minimum and that is convex? 0? That's awesome. Yep. Okay. Now, it's a great function, yeah. Okay. It's the simplest one you can think of. Can you think of something a little bit more fancy? And don't say 1. Okay. What's more complicated? Basically, something that's not a constant.
Constant square.
Exactly. Like your bathtub. Right? This is a function that has one global minimum, and that has many, many minimizers. Okay. Can somebody tell me a function that is convex and that doesn't have a minimizer? Exactly. Very good. So this function here, right? And sorry, I'm not as good as MATLAB. So I know that at 0 it's 1, and at 1 it's going to be e. Right. So this function here does not have a minimizer. It's minimized at minus infinity. It's bounded from below by 0. That's nice. But so that, you can't always have everything. One of the useful functions that we will deal with quite often is the logistic function. So that's log of 1 plus e to the minus x. So this thing also has that kind of property, right? It's a little bit better behaved. It's linear here and then essentially linear, and then it goes like so, and it will never reach 0. Okay. So the couple of useful things. The vertex of a convex set is just a point from which you can't, extrapolate further. Okay? So, in other words, if I make any line that contains this point and something else, and I try to extend it beyond that point, then I'm out of the set. Can somebody tell me the vertices of, well, let's say this ellipsoid? What are its vertices? Exactly. So vertices don't always have to be, have to have edges like this guy here, right? Why am I mentioning this? Because you can always reconstruct the entire set from its vertices. So therefore, if I was to give you a couple of points and I told you, well, draw me the convex hull, then all I do is I just draw that parameter around it. So let's do that here. All right, oops, quite a few points. Now, obviously, you don't do this, so it would be horrible. Instead, you do this. This is the convex hull. This point is contained in the convex hull. It's another nice property of convex hulls that if I have a few extra points in there, they don't matter. Okay. Another really useful thing is that the supremum over a convex set is attained at one of its vertices. So usually convex maximization is an ugly problem. But in some cases it's actually quite nice because, for instance, if I have a convex function, I want to maximize it over a polyhedral set, and I can actually walk through all the vertices, then my optimization algorithm is very simple. Okay, can somebody suggest how I would do that? If I want to maximize a convex function over this set, what's the algorithm to do this?
Start with one vertex and then move to the next.
Exactly. So you just go through all those 5 vertices, evaluate the function, you pick the largest one. It's about as primitive as that. Okay, the bad news is if I have a lot of vertices, this can be hideously inefficient, and there is no way around it. But if the number of vertices is well controlled, you have a very efficient algorithm. If not, then you should change the question that you're trying to ask. Okay, that's basic convexity, about as simple as it gets, and you should never forget that. Okay. Any questions so far? Yes?
Can you walk through why the maximum has to be on a vertex?
Okay. So, well, assume it was not on a vertex, right? And it's a convex function, right? So, all you do is, okay, let's say this is our maximum. Then, well, let's just take a line, right? Now, one thing that we know is because it's a convex function, so I can pick those endpoints, right? And you say this is the maximum. Then, let's look at the epigraph. These are the endpoints. This is our maximum. But, okay, it attains some values here, whatever. It attains a larger value there. So this is not convex anymore, right? So the proof by contradiction is very simple. Okay, good question. So here's the simplest algorithm to actually solve those problems a little bit slightly larger scale. So we already looked at gradient descent, and we actually did stochastic gradient descent. Now if you have moderately low dimensional problems, and with moderately low dimensional I mean a couple of hundred dimensions, you may actually want to look at something that's called the Newton method. So yeah, this, if anybody hasn't seen that yet, that was Mr. Newton, and actually Sir Isaac Newton. And the Newton method is very, very simple to remember whenever you don't remember it. You basically just start by a Taylor expansion. I guess everybody knows what a Taylor expansion is, right? And let's start with something very simple here. We start with a function f of x that's some constant plus a linear term L transpose x plus 1/2 x transposed qx. Okay. Now, this function, we all know, is convex if this matrix Q has only non-negative eigenvalues. Right? So we had a little bit of that in the homework. So, I also know, therefore, that dx of f of x for optimality, so in other words, in order to minimize this, has to vanish, right? So 0 has to be equal to dx of f of x, which is, well, c goes out. So we get L plus q times x, right? That's the derivative. Now if we set that to 0, well, I think anybody can solve it. This is just x is Q inverse L. Okay. Now, this is essentially what we will do in the Newton method. So in the Newton method, if we don't have a function that is a quadratic function, we'll expand it into something.
Minus.
Pardon?
There's a negative sign.
Oh, yes, absolutely. Yeah. Otherwise, it would be horrible. Thanks. I can always expand f into f of x is, well, let's just actually write that as x plus delta. I can write this as f of x plus f prime of x transposed delta plus 1/2 delta transposed f2 prime of x delta plus something that's order of delta cubed, right?
You mean O squared, little o, big O?
Well, what I can do is I can either use the mean value theorem and I get something like, so what I can do is I can bound this with, delta squared within the derivative he has to work, or I have higher order terms. Okay, so we're going to spare ourselves all the mathematical niceties here. This is just intuition. And so, of course, now, if I go and, just ignore this thing, let's just pretend it didn't exist, and I solve for delta, I get exactly this for the update in delta, and so I get exactly this equation here. X goes into x minus, so correct sign, inverse of this thing, and that here. So you can now immediately see why convexity and having that second derivative have non-negative eigenvalues is a really good idea. Yes?
So I didn't quite get that step. In the above Taylor expansion you wrote, I imagine Q is a derivative at some different point, not exactly at the point, because you have equality over there. That means it's not exactly at the...
Well, what I did is that's exactly why I had those higher order terms. Right? So basically this is an approximation plus then some other stuff that I conveniently choose to sweep under the rug. And what we now need to do for the convergence analysis, we'll actually need to worry about this stuff that I just swept under the rug. That's on the next slide. So you're absolutely right. Without this, it's not really an equality. It's an approximation. So quite often, those Taylor series expansions are extremely useful for designing efficient algorithms, because what I can do is I can turn a problem that looks really complicated into one that's only linear and quadratic. For that, we usually know how to solve it efficiently, and then I just pretend the rest didn't exist, and then I need to show that this rest isn't going to ruin my day. That's a very common trick for design and analysis of algorithms. For instance, if I have algorithms that need to deal with some delays, I basically design the algorithm as if the delay didn't exist, and then afterwards I need to prove that the delay isn't going to ruin everything. Right? Or if I have a stochastic gradient descent algorithm, I could essentially argue, well, okay, my gradient's almost the same as the true gradient plus some other stuff, and then you need to control how big that other stuff is. So this is a very useful principle. We're going to see it in action now. Okay. So, yes? Yeah, we will be almost done in 5 minutes. Yes. So here's a very simple thing that you can do. Well, for the convergence analysis, well, now let's actually see what happens to these residual terms. Well, since it's a Taylor expansion and things are differentiable, at least there has to be some region where the residual is, at most quadratic, like gamma times x star minus x squared. Right? So, I don't know what that region is, but I know that once I'm within that region, things are not too horrible. So now what I'm doing is I just expand the Newton update. Right? So this xn plus 1 at the next iteration step minus x star is like xn minus x star minus, here's my update step. Okay, with a little bit, further ado here, I basically can reduce this to the original difference squared and then the Hessian, so the second derivative at this location. Now, here's the thing. Two things can happen. Either this bound is utterly useless, or the bound is useful, right? Okay, duh. Sounds terribly deep, but here's the thing. Whenever, we can pull this out into, this quadratic term, and basically whenever this term here is small enough, then I will actually get quadratic convergence. So that's the good news. So basically, whenever this kicks in, then convergence is amazingly fast. Whenever it doesn't work, then we have a simple gradient descent behavior, just like a simple gradient descent algorithm. So what you can see from that is that essentially, initially when we're really far away, well, this very nice bound didn't really work. And so we are not much better than just doing dumb gradient descent. As soon as we're close enough, the Newton method gives us this wonderful acceleration. Okay, so look through the numerical analysis books, or for instance, Boyd and Vandenberg at chapter 9.5, for a much more formal analysis, which I can't do in the next 3 minutes, but I'll just show you the pictures. So essentially what the Newton method does is it redistorts the space. It rescales it in such a way that, then in this rescaled space, the gradient descent step is a lot faster. So this is the wrong space, and this is arguably a little bit less wrong. Now, what's the good news about the Newton method? Well, one of the things is it's fast once you're close enough, right? Well, the bad news is it may take you quite a while until you get close enough. Secondly, it requires that you invert a matrix, or rather solve a linear system of equations. So if I have a d by d matrix, what's the cost for solving a linear system of equations in d by d? d cubed, exactly. So that's why I said if you have 100 or maybe a couple of hundred dimensions, that's okay, because your cell phone can handle that. But since it grows cubically, very soon your laptop won't be able to handle it. So, maybe 5,000 by 5,000 is about where your laptop will get very warm. And 10,000 by 10,000, you will probably run out of, memory. Okay. You can do a lot of things there where you aggregate Hessians and gradients and do a lot of things. And this is actually the blueprint for a lot of the early distributed optimization algorithms that were published about a decade ago.
Keep all the matrix off.
Okay, that's odd. Because I didn't set the timer. Okay.